I'd like to start with a very long set of words of welcome, especially to our speaker, Tommy Flowers, and all of his colleagues of Bletchley Park, especially Jork Andrews, who worked on the Colossus and also worked on code breaking. After the lecture, I think we'd like to get a group photograph up on the mezzanine where there is a Colossus exhibit. I'd also like to welcome other guests here, two groups to name specifically, the AFIPS History Board, who had their meeting here today, and then the Charles Babbage Institute Board, who's going to have a board meeting tomorrow. There's, I understand, interlocking directorates there on the two boards. And so we're very delighted to have them, and hope that this can at least be an annual occurrence. I certainly want to welcome back all of people who attend the series, and I'm really delighted to see a lot of new faces here, and hope that you'll continue to come. I'd like to point out we're inaugurating the renaming of this room, or I'll say an aliasing of the naming of this room, to be the Hall of Computer Pioneers, who's also the alias as the Marlboro Cafeteria. But the reason it's getting that other name on it is that on the mezzanine we've moved a lot of the historical timeline panels, and I hope you'll come over and look at them if you haven't looked at them already, but look at them during the reception. There's also an exhibit in the back of the room which was loaned to us for a month on Faraday and Maxwell, called Lines and Waves. It's a traveling exhibit. And then if you haven't seen them, there are two Enigma on display at the base of the stairway here. And then in the museum proper, we have a new display on supercomputers, and including, I guess there are about 3 machines there, or not really 3 machines, but parts of 3 machines, because after all, these are supercomputers, and especially including the CDC 6600 number 1 that was loaned to us from Lawrence Livermore Lab. Now I'd like to introduce Morris Wilkes, who is the senior consulting scientist here, responsible for coordinating our scientific effort with our external research program with the various universities. It's fitting that, for 2 reasons, that Morris performed the introduction. Morris gave the inaugural Pioneer Lecture 2 years ago in this museum, and which opened the Digital Computer Museum. And then the other thing is that Morris is really most qualified to introduce Dr. Flowers. So Morris, will you say a few words, please?
Thank you, Gordon. I've known Dr. Flowers for a very long time. He is a modest man. Well, that is true, but what I really mean to say is that he used to work for a very modest organization. And when I first knew him, I did not know about his distinguished work during the war at Bletchley. If I had, there were a number of things I would like to have talked to him about. He's going to tell us something about that work, and I believe he has some new things to tell us that have not been told before. There are a number of things you have to do, my friends tell me, if you want to break other people's code. Of course, you have first of all to, you remember Mrs. Beaton said if you wanted to cook a hare, you first had to catch the hare. You first catch the messages that you would like to try and decode, and then you must break the key, And that, as I understand it, is the function of the machine that Dr. Flowers is to talk to us about. It was a special purpose machine, and that was its special purpose. Nowadays, you would have a general purpose machine that could perhaps go on to do the actual decoding, but I understand that that was not the state of the art then by any means. And then, of course, lots of other things have to be done to make use of this information that has been revealed. Now, Dr. Flowers has had a distinguished career apart from his wartime work in telecommunications, partly for the British Post Office and partly for the telephone industry. And since his work has become known, he's received a number of honours, the Thomson Medal of the IEA, an Honorary Doctor of Science of the University of Newcastle on Tyne, and one of my last public engagements before I left England to come to America something over a year ago was to attend a dinner at the Savoy Hotel in London given by the British Post Office. Sorry, it was a luncheon. And at that luncheon, Dr. Flowers was presented with the Martyrdom Medal as a recognition of the work that he had done for the Post Office and for the United Kingdom. Dr. Flowers, it's a very great pleasure to invite you to give your address.
Mr. Chairman, ladies and gentlemen, during World War II, I became involved in code-breaking activities, as has already been stated, and in that activities I conceived and built machines which became known as Colossus. And no mention was made of these machines at the time, and it was 30 years later that Brian Randall, the professor of computer science at the University of Newcastle upon Tyne, chanced to hear about them. All the record that then existed, maybe just a little bit closer to you. Up close. That's all the record of the existence of these machines, which was then available, was in the memories of those who were involved at the time and still surviving. Many of these Brian Randall was able to meet and question, by which means he gained enough information to piece together a description of the construction and operation of the machines. And realizing that they were in fact electronic data processors, it was he who raised the question of their relevance to modern computers. That Colossus occurred at all was due to a series of lucky chances, to which one more is added if because of it I'm to be numbered among the computer pioneers, because at the time I had no thought or knowledge of computers in the modern sense, and had never heard the term used except to describe somebody who did calculations with the aid of a desk machine. The real origin of the Colossus machines was the work which I did before the war in the laboratories at Dollis Hill of the Post Office, which in Britain, if you don't happen to know, runs the telephone and other communication services as a country. And soon after I went to the laboratories in 1930, my researches were directed to finding the reasons why so many of the calls dialed by the public gave wrong connections or no connections at all, which I think was a phenomenon not confined to my country. I think my reaction to this work was that a very young engineer of the time, which was, if this system doesn't work very well, how do we make a better one? And by 1935, I had become interested in electronic switches as an alternative to the electromagnetic switches which were then in use. And this was not so remarkable as it might seem, because copper oxide rectifiers and thermionic vacuum tubes had become plentiful and cheap during the 1920s, and by 1935 were being used as switches in a variety of applications. In speech and radio transmission systems, they were used as modulators for their high switching speed, and in telegraph transmission systems, they were being used as relays, not because of their high speed, because it was low speed operation, but because of their reliability, which is just what I was looking for. High-speed counters using tubes had been invented in 1939 by Wynne Williams for scientific experiments at Cambridge University. And as far back as 1919, the Eccles-Jordan trigger circuit had been published, but was practically no use having been made of it, even though that it could be used as a relay and as a one-bit store. I'm sure that when I use modern terms like one-bit store, programmer and so forth, you will understand that these were not terms in use at the time, but I'm using them in the hope that they will make what I'm saying easier for a modern audience to understand. So from 1935 onwards, I was exploring the uses of electronics in telephone exchanges, and by 1939, I felt able to prove what up to then I could only suspect, that an electronic equivalent could be made of any electromechanical switching or data processing machine. And I well remember the elation that I felt when I reached that point, because it meant that not only could parts of telephone exchanges be electronic, but the completely electronic exchanges were possible, which is a new and somewhat exciting concept. However, something more than equivalence was going to be needed, because the electronic exchanges based on that principle of equivalence were much too costly to be used in practice. I knew nothing of similar ideas which were being pursued in other parts of the world, because none have reached the stage of publication. And this was then the state of the art as far as I was concerned when hostilities commenced in Europe in 1939, and all civil work in Britain had to be subordinated to war work, in the course of which I was sent to Bletchley Park, a highly secret establishment some 50 miles north of London, to take on some top secret work. And that was in 1942, and by good luck I was about to be involved in code breaking and would encounter a problem for which my pre-war work would be needed at no matter what the cost. From about a year or so after the war had started, cryptanalysts at Bletchley Park had been reading German messages which had been encoded on a machine called ENIGMA. Alan Turing, whose picture is up there, and whose name familiar I'm sure to most of you, was a leading figure in this activity, and it was he who explained it to me and what the post office was required to do, which was something that any telephone manufacturing could have just as easily have done, and was soon found not to be needed anyway. Had that been realised earlier, and there was some suspicion that it could have been, Dollis Hill might never have been involved with Bletchley Park, and although the final outcome of the war would no doubt have been the same, its history could have been very different with greater loss of life and damage. But I and two other Dollis Hill engineers, Sidney Broadhurst and Bill Chandler, had become involved, and we were available when a new engineering problem arose. The Germans had invented a machine to encipher teleprinter messages using a principle invented by an American, Gilbert Vernon, in 1917 during the First World War, but had scarcely been used up to that time because of operational difficulties. The German machine looked like and was operated like a teleprinter, but it differed in that messages sent in plain language from the keyboard were transmitted by the machine in cipher, and in ciphers messages received into the machine came out printed in plain language, all automatically without effort on part of the machine operator, other than setting the machine to to some initial mechanical conditions specified in the code book before sending or receiving a message. Operationally, nothing could have been simpler. Bletchley Park received the messages on 5-hole punch tape, as shown in this picture. The tape itself could have been anything up to 200 feet in length, generally much shorter. So the picture can only show the two ends of the tape. And each character is a 5 binary digit number represented by holes in lines across the tape, together with a small sprocket hole by which the tape is driven so that they may be punched or read. And the sprocket hole comes between the second and third elements, second and third digits of the characters across the tape. Bletchley Park, for its own purposes, put 2 other holes into the tape, a start hole at the beginning between the third and fourth digits, and a stop hole between the fourth and fifth digits to indicate to the processor when the message was about to start and when it had ended. A punch was specially made for the purpose of putting the start and stop holes into the tape has the description of distinction of being one of the few surviving relics of the Colossus machine, and it is in fact in view over there. The enciphering and deciphering within the machine depended on 12 code wheels, round the peripheries of which were 2-position cams, which could be set by hand to one or other of 2 positions. In this picture you can see that the cams are rods which can be pushed from one side of the disc to the other, and whichever position they are pushed by hand, they're clamped in position. And by these means, each wheel stored a pattern in binary code, the numbers of digits in the patterns being all different due to the wheels being of different diameters, and all primed to one another to maximize the number of different relative positions of the wheels. This code wheel, this is a very simplified picture of course, has only 7 cams around the periphery. The actual wheels varied in size from something over 20 to something over 50 cam positions around the wheels, and as I said, they were all different sizes and all primed to one another. And as the wheels were rotated during the transmission of a message, the cams operated contacts to vary the 5 digits of the teleprinter code in a pseudo-random sort of way. In this slide, the plain text value of the digit for the character sent without encipherment, that is to say, the character sent by the teleprinter is represented by the contacts A, which in binary notation can be 0 or 1, and depends and is in one or other of the positions depending on the character to be sent. The value of the contacts B operated by the cams, the contacts B, are operated by the cams of one of the code wheels, and can also be represented by 0 or 1. Let's say the contacts can be in one or other of their 2 positions depending on the cam which is operating at the time. And the output from the contacts B is the modulo 2 addition of A plus B by table up there, modulo 2 just being addition without carries, you all know. The cams, the contacts C are contacts which are operated by another cam wheel and does a second modulo 2 addition, and the output from the contacts of C is the enciphered digit to be sent. The electronic equivalent of the context B is shown at the bottom of the slide. I don't propose to describe any of the circuitry except for one important one which will come later, but you can see that it requires 3 tubes and a few resistors and capacitors in order to be the equivalent to the context and to do modulo 2 addition. That slide represents the encipherment of just one of the 5 characters, one of the 5 digits of the teleprinted code. For the 5 digits of the teleprinted code, there were 2 sets of 5 wheels which operated on the chems B and C. One set of 5 wheels operated chems B, and the other set of 5 wheels operated chems C. One of the sets of wheels took 1 rotational step for every character that was transmitted. The second set stepped not for every character, but erratically, as determined by the chems on 2 further wheels, making a total of 12 wheels. The number of combinations of different wheel positions, and therefore of characters, which could be transmitted before the cipher repeated itself, was so great that in practice it never did repeat, which gave the enemy such confidence in the invulnerability of the messages enciphered by these machines that the machines were used to send information of the highest importance, such as battle orders in great detail, and even messages and instructions from Hitler himself to his field commanders. Late in 1942, to work on the German teleprinted traffic. The problem was to find first the wheel patterns of the wheels, which were then in operation, and which at that time were being changed periodically, and then the starting positions of the wheels for every message which was received. Two-part problem, the patterns of the wheels, and then the starting positions of the wheels for each particular message. Newman had the idea that a key tape representing some characteristic of the coding machine and formed into a loop could be processed with a message tape also formed into a loop, and if the processing were repeated as many times as was necessary for every possible position of the key tape relative to the message tape to be tested, then some clue might be obtained. To keep the 2 tapes in synchronism, they have to be driven by sprocket wheels, the mechanical sprocket wheels, as you can see. And in order to that, what was completed with repeated running, the key tape shall occupy every position relative to the message tape. That could be simply arranged by making the number of characters in the 2 tapes prime to one another, and then in course of time they will go through all the possible combinations. With one clue and another key tape, another clue might emerge. This was Newman's idea, and continuing in this way, enough clues would lead to a solution. The quantity of processing was manifestly exceedingly large. Hence, even to test his theories, some kind of machine had to be devised, and it was easily calculable that a machine using the fastest techniques of data processing available at that time would take much too long to produce operationally useful results. Electronics was therefore clearly necessary. Some kind of machinery. A man from Dollis Hill, a man called F.O. Morrell, who was an expert in teleprinter engineering, was given charge of the project. The loops of tape were much too long to hang freely, and therefore some sort of structure had to be I hope it was devised to run the tapes. The tapes, the structure was the thing with pulleys. It's not very clear from this picture, but I'll show it again later on. Some of the pulleys on the side are 2 or 3 pulleys side by side. They're all loose pulleys, you see, so that the tape could be wound round in many loops. One pulley, the one on the right-hand side, was variable, so that you could take up the slack, and in that way, the tapes could be run. 2 tapes were necessary. You can see there are 2 tapes. There's substitute 2 tapes. Photoelectric reading was the only possibility to read the tapes, to read the tapes at the speed at which they had to run. And 2 Dollis Hill physicists, Eric Spate and Arnold Lynch, designed, and the model shop at Dollis Hill made, a photoelectric reader, which was very similar to a cinematograph projector, but working in the opposite direction, by projecting from the outside inside, from a lamp and an optical system on the gate to a screen inside the machine. The screen of which really was a photographic plate, which is opaque except for some clear spaces, behind which photocells were located, photocells and amplifiers were located. This screen is really a mask to control the amount of light which reach the photocells as the images of the holes in the tape move across the plate. The crescent-shaped spaces in the mask were designed so that circular areas of light derived from holes in the tape and moving from left to right across the screen would produce generated approximately rectangular output pulses from the photocells and amplifiers. There were 10 photocells in 2 rows of 5, which were the big ones, the crescent-shaped ones, which enabled 2 successive digits, 2 successive characters on the tape to be read simultaneously, because that was a necessary part of some of the processing. The sprocket holes produce a continuous output from pulses from another cell and amplifier. That's the little one in the middle. And the slits above them at the top half of the mask were detected the start and stop holes, which came between the 3rd and 4th and the 4th and 5th digits. Driving the tapes by sprocket wheels was tried experimentally as soon as a bedstead. The thing with pulleys on it was known as a bedstead, a double bedstead, as it was too bad. The tape driving was tried as soon as a bedstead became available. And to give some idea of the problems involved, excuse me, typical tapes would be 5,000 and 1,000 characters long, for which one complete program of processing would require the first one, the 5,000 character tape, to make 1,000 revolutions, and the 1,000 character tape to make 5,000 revolutions to do one complete program. And it seemed, even without actually trying it, that the chance of paper or any other kind of tape standing up to passing over the sprocket wheels that number of times without damage were somewhat remote. And the initial tests were in fact distinctly discouraging. if the tape was accelerating too fast, the sprocket holes tore the tape down the middle, and various things. Also, the joint where the tape was stuck together was a terrible problem. And various designs of sprocket wheel were tried with no conspicuous improvement. And with diminishing prospects of ultimate success, some new ideas began to be urgently sought. And it was at this point that I realized that my pre-war work pointed to a solution to the synchronization problem, which was simple in principle, although it might be difficult to put into practice. It was not the paper tape that was essential to the processing, but the data on the tape. All that the key tape was doing was storing pre-generated data so that they could be read into an electronic processor at a high speed. An electronic equivalent of the machine that had originally generated the data, and I had no doubt that such an equivalent could be made, could work fast enough to issue the data directly to the processor and thus render the key tape unnecessary. Only one loop, that of the message tape, would then be needed, and that would be driven by smooth face pulleys at high speed without much fear of damage. And moreover, the considerable trouble, time and labour needed to make key tapes and to load them into the machine in exact relationship to the other tape, which was quite a difficulty, would disappear. Well, this suggestion was made in February 1943 and was received with considerable scepticism. It was thought that a machine with the number of tubes that was obviously going to be necessary would be too unreliable to be useful because of the believed high fault liability of tubes. But the post office is a large user of tubes, and it was able to knew that the unreliability of tubes was associated with tubes which were in equipment which was being continuously moved and switched on and off. But the post office had in its transmission network, in its communication network, thousands of tubes which were stationary, never moved, and never switched on and off, and we knew that the reliability of those was a very high order. But then it was thought that as the machine would be novel, there was no precedent for it, that it would take such a long time to design and manufacture, that the war would be over before it could be operational. And to that the post office said that they thought they could make such a machine in 1 year, and it was unlikely that war would be over by 1 year's time, which was February 1944, which in fact we know it wasn't. Finally, we were asked if we could guarantee that if we made this machine it would work, and of course, as there was no such machine has ever been made before, we couldn't guarantee that it would work. So it was decreed that work on the two-tape machine should continue and have first priority. And what to do about a one-tape electronic machine would be left to those who had to make it to decide. Events justified this decision because machines with two tapes operating in synchronism at 2,000 characters per second and synchronized by sprocket wheels were in service operation from about the middle of 1943 and were codenamed Robinson, after Heath Robinson, a well-known cartoonist, well known for his drawings of ludicrous tasks performed by fantastic machines. The tape running problem had been solved by motoring one of the smooth pulleys to relieve the sprockets of most of the driving, but they were still able to maintain synchronism. Much valuable work was done by these machines toward validating and developing the ideas of Newman and other mathematicians who had been recruited for the project. The quantity of messages decoded was small in relation to the total traffic, but they were nevertheless important. Meanwhile, the Dollis Hill engineers, having decided to make an all-electronic processor, took only 10 months to get the first machine into service, a feat made possible by the absolute priority that they were given to command services and materials without any questions being asked, but mostly by the prodigious efforts of the laboratory staff, many of whom did nothing but work, eat and sleep for weeks and months on end, except for one half day per week they allowed themselves for the necessities of life, such as talking to their wives and getting their hair cut. The United States also contributed to the first machine in the shape of tubes and an electromagnetic typewriter, which was supplied under the lease lend arrangements which was then in force. Responsibility for the overall and the detailed design of the first machine was shared between Sidney Broadhurst, Bill Chandler and myself, with Alan Coombs joining us somewhat later for later design and construction work. The first machine went into service in the early part of December 1943 and was codenamed Colossus by Bletchley Park because it was the largest machine that they'd had to operate up to then. The cryptanalysts were impressed by the speed of the machine, which was 5,000 characters per second, and by the reliability, which soon gave them every confidence in the results produced. And as the cryptanalysts became more familiar with the machine and its greatly increased processing power compared with the Robinsons, so ideas for new processes occurred, some of them being impossible of execution on the previous Robinson machines. The practical speed at which Colossus could be operated was tested by loading it with a maximum length tape and increasing the speed until something happened, completing the motor speed until something happened. And at about 9,700 characters per second, the tape broke in one and then in several places, and the various sections then did their best to obey Newton's first law and travel in a straight line in whatever direction they happened to be going, with an initial velocity of nearly 60 miles an hour, and thus finished up in all sorts of curious places. 5,000 characters per second was clearly the maximum, which was like the maximum safe speed, but a much higher speed had been foreseen to be necessary if the numbers of machines which eventually had to be made and the staff to man them were to be practical sizes. And that prompted the idea that the effective speed could be increased by parallel processing. By using 5 processors in parallel, all operating on the same program, but with different input data from the tape, an effective speed of 25,000 characters per second was obtained, and that was enough. 5 separate processors presented little difficulty, but a photoelectric reader, to supply them with data, would have to have read 6 lines of tape simultaneously, and that was going to be very difficult to construct. 6 lines were necessary so that 2 consecutive but different lines from the tape could be presented to each of the 5 processors. And this difficulty was solved by a shift register, which was invented for the purpose, so that data read from the tape were read into 6-bit shift registers, which meant that 6 consecutive characters from the message tape were available for processing using a tape reader which had to read only 1 line at a time, and thus was simplified compared with the tape readers which had been used on the Robinsons. Excuse me. It had been very evident from very early on that if the first Colossus was successful, several more would be demanded in a great hurry. So even before the first was finished and working, a redesign incorporating improvements and new ideas was got underway, and the manufacture of parts was started, particularly of those parts which took a long time to make, which was just as well, because at about the end of February 1944, I was told at a meeting at Bletchley Park that 12 machines were to be in operation by the following June the 1st, which was just 3 months ahead. The instructions had come from the highest level, and I well remember the consternation when I had to say flatly that it was impossible. This sudden demand had stemmed not only from the success of the existing Colossus machine, but also from the increasingly widespread German use of teleprinted enciphered messages, together with improved operating procedures, which meant that we had to work much harder to achieve the same results. It was promised that having a good start because of the parts already made, the laboratories would make 1 or 2 machines and have the first in service by the required date of June the 1st. And for the remainder, the post office, a factory which we controlled in Birmingham, would have to be organised to make most of the parts for assembly by Dollis Hill, by which means delivery at the rate of 1 per month after the first was working was thought to be possible. So after another period of intensive work by all concerned, the first of the new machines was operational on May the 31st, except for being subject to intermittent and mysterious faults, which made it completely unworkable. But just after midnight of that day, the commissioning team decided they were too tired to go on and went home to have a few hours sleep. And when they returned at 8:30 the next morning, which was June the 1st, the due date, they found the machine actually in service. What had happened was that a Dollis Hill engineer who was stationed at Bletchley Park and happened to be on night duty that night had discovered the trouble to be parasitic oscillation between the heaters and the cathodes of some of the tubes, a very difficult fault to find, but one which had been cured very simply by the addition of a few resistors. I've included these few details of what actually happened in the hope that they may convey in some small way the dedication, the excitement and the job satisfaction of those hectic days. The remainder of the machines did in fact follow as promised, so that when the Germans surrender 11 months after June the 1st, 1944, put an abrupt end to the whole enterprise, 10 machines were in operation and the 11th was about to be commissioned. Excuse me. Turning now to the actual construction of the machinery, a principal element of Colossus was the bitstream generator, which replaced the Robinson key tapes. This comprised a bank of 12 counters of different scales, which generated the my voice is, excuse me. A bank of 12 counters of different scales, which generated the bit streams from semi-permanent data stored with the rings. The bitstream generator and the reading of the tape and the data processing were necessarily all electronic to attain the processing speed required. But electromagnetic telephone exchange type switches were also used in large quantities for lower speed operations such as readout and print, simply because that was the quickest and best way of making the machines. The first Colossus had contained 1,500 tubes. The production machines needed 2,400 tubes because of their increased processing power and facilities, together with 12 rotary switches, mechanical rotary switches, about 800 relays, and an IBM electromagnetic typewriter to print the output. And the semi-permanent data of the ring stores was read in by U-links inserted by hand into pairs of sockets. On this picture, I hope you can see it right at the bottom. There are sockets into which pairs of sockets into which U-links could be inserted by hand, and the data were read out by thyrotron tubes connected in series to form a ring operating as a Wim-Williams type counter. Thyrotron tubes, as I expect most of you know, have a grid electrode by which they can be fired. As I say, they can be made to conduct current from the cathode to the anode. And once fired, they will remain fired until the power supply to the tubes is cut off. You will see that for each pair of sockets, a thyrotron tube is connected, such that when the tube was fired, it caused current to flow to the output of the ring if the socket contained a U-link. Only one tube could be in the fired condition at any one time, and as pulses to be counted were received, the fired tube moved step by step round the ring. At each step, one bit of stored data was read out to the output, which I think you can see. There's only a portion of the ring is shown in this picture, of course, and as each thyrotron is fired, so it communicates current to the output, but only if it had a U-link in its put in the socket. A clear pulse applied to the anodes of all the thyrotrons of all the rings ensured that none was in the fired condition. And then a negative pulse was applied through the start address switch, which I will mention in a moment, which caused one of the thyrotrons in each of the rings to be fired. The start address switch decides where the counting is to start from. And in operation during processing, when one revolution of the message tape and scan of the message has been completed, a clear pulse was applied to the anodes of all the thyrotrons, so that there was then no thyrotron was struck, and then a negative pulse was applied through the start address switch to fire one of the tubes, and the rings then, which have been prepared in that way, were then ready to count sprocket hole pulses occurring between the start and the stop holes of the machine tape, some rings receiving all the pulses, and other such sprocket hole pulses as the logic allowed to be transmitted to them. The rings ceasing to count at the end of the message, they were prepared for the next scan by the clear and the start address, which is pulses which I've just described. The start address switch, which you can see at the top, was an electromechanical rotary switch with an arm which connected in turn to the cathodes of all the thyrotrons in the ring. And the contact on which this switch stood at any one time marked the position from which stepping was to start for the next scan of the message. And this point was indicated to the output printer by wiring on additional banks of the rotary switches, but not shown in this picture. There were other banks of the switch with wiring which went to the printer to indicate the number of the contact that it was standing on. For any one program, the point could be constant for all scans throughout that program, in which case the start address switch was positioned on one contact, in which it remained for the whole of that program. Or the point could be progressive, that is to say, the switch would stand on one point, one contact, and start the ring in that position for one scan. During the scan, the switch would move one step round the bed, so that for the next scan, the switch would the ring would start at the next point round the ring. So that in time, every thyrotron in the ring would be the position from which the counting started for a particular scan of the message. Yet another alternative progression of the start address switches was used if parallel processing was in operation, because instead of taking one step between scans, it had to take five steps. And for each program, the programmer had to select and arrange for one of these modes of operation to be effective. And the actual stepping of the switches, as I said, took place while the processing was in operation. The simplified schematic of the machine shows bit streams C1 to C5. I hope you can see them on the left. And they are the five elements, 5 bit streams from the enciphered message, which is read by the photoelectric scanner. The red ones coming from the top of the bit streams from the counting rings, and if they are connected as shown, I hope you can see them, through modulo 2 adders, then what would come out on the bit streams M1 to N5, if the starting positions of the wheels had been the ones from which the message had started, then what came out there would be something would be related to the plain text of the message. The machine was not, however, wired permanently with modulo 2 units as shown there. All the bit streams were taken into the data processor, where there were switches which were connected the bit streams to function units, and finally to an output printer on which the output data, the result of the processing, was printed. The function units included not only the modulo 2 adder, which I showed earlier on, but also a Boolean adder, which needed only 2 tubes. There were inversion units, which just logic converters, which required 1 tube, and an Eccles-Jordan 1-bit store, which used 4 tubes. The actual Eccles-Jordan circuit is the 2 tubes in the middle. The tubes at the outside just set it to set the trigger to one or other of the 2 positions. The shift registers, which I mentioned as being used for the output for the store, were made by putting 1-bit Eccles-Jordan units in series, but connected through delay networks, which were simple resistors and capacitors, which, as I think everybody knows, is one way of connecting them together. The counters, which were used in the processing, for the output processing, were not thyrotron type, they were too slow, but were vacuum tube counters. And vacuum tube counters cannot easily be made to count in scale of 10. And so each decade was made up of 1 scale of 2 and 1 scale of 5 counter in series, what used to be called biquinaries. And I think there is a picture of it up there. The outputs from the counters were thus given on 7 wires, and not although they were decade. The outputs from the counters were thus given on 7 wires from the 7 tubes of the counters, and they had to be decoded by relays to decimal equivalents for the output printer. The mode of operation of Colossus by a cryptanalyst was to set up a program and run it, and use the result of that program to set up the next, and so on, until all the required information has been obtained. The full schematic diagram, which doesn't need to be counter rings, which are producing the bit streams from the ring counters. They are at the bottom there, and the bit streams from the tape, from the message tape, and from the ring counters were clocked by pulses into 6-digit, the message tape into 6-digit shift registers, which I don't know whether there's only five outlets shown that should be 6. And also the same clock pulses clocks the bit streams from the ring counters into 1-bit stores, so that the ring counter data and the message data were in synchronism because they were clocked by the same pulses. This is a bit, yeah. The message tape produced continuous sprocket pulses, which were supplied to the master control. And when this start pulse was received from the tape, the clock pulses, the sprocket hole pulses, were then supplied to the ring counters, so that the sprocket hole pulses which occurred between the start and the stop hole on the tape controlled the processing. I'm sorry. Yes, only one processor is shown on this this slide because it's too difficult to show the others. And you will see that the message tape data and the ring counter data are connected to programs switches, where they are then connected to, as according to the program, to function units, which are, if you can see at the bottom there, see. And the sprocket hole pulses, which are released by between the start and the stop signal, are also form one series of pulses. Then there's another series of pulses, CO2, which you can't see very well, which are interposed, which come in between, they're interlaced between the CO1 pulses, so that the CO1 pulses can start an operation, and the CO pulses can then clock it later on when that operation is finished. The output from the program switches, as I say, that at the bottom there, on the bottom line, was the result of the processing, which was pulses which would be counted by a 4-decade counter, output counter on the right, and the pulses from the processing were supplied to what is called an add-1 unit, and they were clocked by a CO2 pulse into the counter, which added them all up, but only if there's a third connection at the top they were permitted to do so by a third connection to the top, which I will mention in a minute. Now the counter thus accumulated, the 4-digit counter thus accumulated all the pulses which resulted from the processing during one scan of the message. And normally the total that was accumulated was not of great interest. It was only the high counts which were of interest. And in order to print only the high counts, the output counter, the 4-decade output counter, had 4 switches, which could be decade switches, which could be set by the programmer to a number which was a set total, and only if the set total was exceeded was the result of the processing printed out. So what usually happened was that during the one scan of the tape, when the start pulse was received, it started processing with the CO1 pulses and the CO2 pulses. At the end of the scan, the stop pulse would cause the master control to send out to the output a read, a test counter pulse. The test counter, that would test the number which had been received by the counter. If the set total hadn't been exceeded, which was the usual case, then it just went on to the next scan of the tape. In between the stop pulse and the start pulse, it reset the wheels of the ring counters by a clear pulse and a start address pulse, and it would go on scanning the tape with different start positions of some of the wheels until the set total was exceeded. Then when the set total was exceeded, then it would send a pulse to read. The readout would then read the number that was had been accumulated on the counter. It would also cause the positions of the start address switches for that particular scan also to be stored in the readout, and then the printer would print out all that data while the processing was going on, because it would then the tape would still go on to the next scan. To run one program, the programmer selected the ring stores to be used and set them to operate in the required start address modes. And this operation also prepared the selected rings for the first scan of the message. The programmer then operated the program switches to set the required program and the output counter to the set total which he had chosen. And more often, the cryptanalyst in charge of the machine wrote the program in symbolic notation on a slip of paper and gave it to a wren to execute. Our wrens were your waves, I think. The women's, they were the women's sailors. Each machine was manned by 2 wrens who prepared and loaded the tapes and attended to the running of the machine, including the setting up of given programs. The program being set, the message tape motor was switched on, and when the tape had reached running speed, a menu start switch was pressed. The processing started with the receipt by the master control of a start hold pulse, the CO1 and the CO2 pulses following the start pulse caused the program to be executed, and on the occurrence of the stop pulse, and the master control sent a test counter pulse, which I've described, to print out or not to print out, depending on whether the set total had been reached. But usually, because so few of the scans of the tape produced a readout, the printer was ready to receive the data when it was called upon to do so. But occasionally, the printer would be still engaged at the end of a scan, which needed a printout. In that case, the master control would know from the data given to it that the printer wasn't ready, and it would just stop all processing and let the tape go on until another stop pulse was received when the printer was free, when it would then print out, would then go on with the printing out. Of course, the master control, the program control had to be arranged so that all the operations could take place in between the stop and the start pulse, and also the tape had to have a sufficient length of tape to give time for all the operations to take place, and that usually meant that a minimum of 150 characters had to appear in the blank space. But the processing was not always successful. If no result could be obtained from a message, and that happened fairly frequently, corruption of the text in reception was a very possible cause. Corruption of the text could produce false characters, additional characters which shouldn't have been there, or it could miss out some of the characters which should have been there. And if corruption was possible in the text, it would make it impossible to get any meaningful result. In that case, processing not of the whole message, but only of a section of it would sometimes be tried. And a span counter was provided for this purpose. It's shown up there. The span counter took all the sprocket pulses, all the sprocket hole pulses from all the CO1 pulses, all the sprocket hole pulses between the start and the stop signal, and it had two sets of dials, sets of switches on it, which could be set to two numbers, by which one number would define the start of the processing. It would how many characters it would receive before it started processing, and the stop character would say when it would stop. So by that means, usually the first half of the message would be tested, and if that gave no result, then the second half would be tested, and if that gave no result, then the middle might be tested. And so that is the control which is on the counter, on the output of the counter. It became convenient as more machines became available to hardwire some of the much used or more complicated programs instead of using the switches to set them up. And for that reason, there were individual variations between the machines which were installed, although they were all basically the same. This shows the front view of a bedstead in which the two tapes can be seen. Although the the Colossus itself didn't need two tapes, the two tapes machines had been constructed for the Robinsons, and the two tapes were continued for the Colossus, so that one tape could be prepared, ready for processing when the previous one had been finished. In a way they saved machine time. Either either of the tapes could have a length up to 25,000 characters, which was just about 200 feet in length. You could see the pulleys on the right, the large number of convolutions that you could get actually in the tape, and could actually get up to a length of 25,000 characters. You can also see if you can see, the electromagnetic typewriter on the stand there, and a narrow strip of paper. On the left, you can see that the set total dials on the 5 counters for parallel processing. On the counters there, up there. The first Colossus had this is the switch panel for connecting up the bit streams to the function units and so forth. On the first Colossus, we used just standard telephone type plugs and cords, and this was the panel of the sockets, the jack strips on which the bit streams and so forth were connected, and the program was set up by double-ended cords which were put into the jacks like an ordinary switchboard. In the subsequent machines, that was retained. It's a panel just there, but particularly for the parallel processing, when the same program had to be set up on 5 different processors, a key panel was used, which is over on the left there, by the second go. That's a closer up picture of the machine. The next picture is the back view. This is the back view of the Colossus, but it's not the back view of the front view panel that you saw. This is a second. There were two rows of racks, and this is the second row of rack. Colossus had features now associated with digital computers, semi-permanent and temporary data storage, arithmetic and logic units, including branching logic and variable programming, which may justify its being regarded as a digital computer. The control of Colossus by wired logic and of a computer by stored program logic, which makes it a general purpose machine, is the most obvious difference. Colossus was a special purpose machine required to attain the highest possible processing speed, which with the technology of the day would have compelled the use of wired logic, even if stored program logic had been thought of at that time. Each switching operation took about 10 microseconds to complete, and the total program time between CO1 and CO2 pulses was much less than 20 microseconds, much less than 200 microseconds. Hence, the number of steps in the program would have been very, very small. Nevertheless, there was enough flexibility in the programming for several tasks for which the machine had not been specifically designed to be executed. I believe, in fact, that it was programmed to do multiplication of 2 5-digit numbers, which in decimal, and produce decimal results. The only trouble was there wasn't enough time. It couldn't get all the steps in the time available. The program couldn't be complete, but it was in fact programmed to do multiplication to some extent. Colossus was comparable in conception and in processing power with ENIAC, which was designed as a computer but without stored program logic, and came into operation some 10 years after Colossus, some 2 years after Colossus. Colossus undoubtedly made a contribution to the development of computers in Britain by showing Turing, Newman and some others what electronics could do, and that knowledge turned their minds to computers immediately after the war. I was not myself interested so much in computers as in telephone exchanges, and in 1946 I discovered that something other than equivalence needed to make electronic exchanges economic was time division multiplexing, but no practical use was made of the discovery until after I had retired, but that's another story. The events which I have been recounting happened so long ago that when I came to think about what I might say in this lecture, I found that I had forgotten many of the details. And this had the happy result that the inquiries that I had to make caused me to contact many of the people who took part at the time, some of whom I had not seen since, which was in itself a pleasure, and the information which they gave me a great help, which I gratefully acknowledge. I'm also greatly indebted to the Post Office laboratories, no longer at Dollis Hill, but on the east coast at Martlesham, for providing many of the illustrations and all of the slides in the lecture. Two quotations provide me with appropriate words with which to close this lecture. The first is attributed to US Air Force General Doolittle when he visited Bletchley Park and gave a pep talk to the staff, in which he said that fighting a war when you can read your enemy's secret messages is like playing poker when you can see your opponent's cards. In the end, you're bound to win. And the second was spoken by Max Newman when the war in Europe being over. He called everybody together to announce that the unit was to close down and everybody could go home. And he concluded by saying that to lose the most interesting and exciting job that we're ever likely to have during our whole lives was the price that we as individuals had to pay for peace.
A couple of comments, and then I think there may be, I'm sure there are questions, but there's a lot of material has been covered, because all of us who've read, I think, everything from Brian Randall's book to the book Code Breakers and all the other popular books about the work at Bletchley Park have always been fascinated by what is in Colossus, and it's amazing that we now have a glimpse of what it was and what it did. I have, in a sense, the first question, and I'm not going to ask Dr. Flowers. I'm going to ask Jork Andrews, who came over here especially for that, who worked for Dr. Flowers on the Colossus, and I'd like him to give a kind of an unbiased set of comments about what it was like on Colossus and what he thinks the effects were on computing. It's not totally unbiased, but
well, I do consider myself particularly fortunate for a number of reasons. Fortunate in the first instance because I was privileged to be able to work for Tommy Flowers about 20 years ago. Not, I'm afraid, on Colossus. I was employed at some other part of British Telecoms at that time. But I was able then to experience the intense loyalty his staff felt for him. This was in part due to his ability to seize on the fundamental issues in any problem and to attack them in a dogged fashion. Solutions were obtained that way in which others might not have thought possible. Certainly, that was the case with Colossus. He also gained immense respect for his ability to take entirely new technologies on board. Now, in those days, 20 years ago, when I was working with him, discrete transistors and square loop cores were the thing, and he took those on board. And I remember that the team used to regard Mondays as a mixed blessing, because those were the days he'd come in with very large sheets of paper, with very detailed circuit diagrams drawn on them, in his own characteristic black ink from a nib pen. Fridays was the other bad day, because that was the time he would discover that in order to make the equipment work and put in the resistors and the decoupling that needed, we doubled the component count and therefore ruined his circuits. That took us back to Monday again. I'm also fortunate in having, as friends, a number of people who did work for THF on Colossus, and they still hold him in the highest regard, the same regard they fought for him 40 years ago. I'm fortunate again because I'm one of the few who will have heard THF describe, that's the way we used to call him, I'm afraid, THF, sorry about that. I've heard him describe this work twice. He first described it to an overflowing lecture theatre, more than 400 people there, at his old place of work, now called the British Telecom Research Labs at Martlesham Heath. Now, as you may know, he's not been free to discuss this work before, but what he now reveals is so surprising, and he presents it in such a matter-of-fact way that some of you may miss some of the points on first hearing. Having had time to mull over his presentation the last few weeks, I've picked out the following contributions which he and the people around him were probably the first to make to the electronic data processing field. So my question to Tommy Flowers really is this list true? It was obviously, we recognise now, the first application of logic controlled by an alterable program. It also appears to be the first use of clock synchronizing pulses to large blocks of logic, the first use of parallel processing, the first use of interrupt, in this case until printer ready, the first use of optical reading of paper tape, the first use of a higher level description of a machine program. Not, of course, the engineers, but the people who use the machines found shorthand ways of describing what they wanted to the wrens, or the waves as you call them. But more incredibly than anything, I think, the first use of shift registers. There must be many like myself who think that the world was created with shift registers as part of the package. To imagine a world without them is quite difficult. There is one more incredible thing to note, that all of these developments were put into service without any prior breadboarding. There just wasn't time. Well, the developments which we've heard about led to military intelligence operations which were so successful that it's now become recognised as a major factor in the outcome of the last war. For all that, Tommy Flowers, we thank you.